This movie has been designed to help you study the physical and operational characteristics of the human ear in some detail. Click on any of the blue menu choices on the left to learn about the ear's anatomy. The outer ear, also called the pinna or auricle, collects sound waves from the environment and funnels them into the ear canal. In addition to its overall function of amplifying sound like an ear trumpet, its ridges reflect sound waves so that there is a slight delay between these waves and waves entering the ear canal directly. The phase differential that this creates changes the sound's tonal characteristics and assists us in sensing its spatial origin. Because the phase differential is proportionately larger for the shorter wavelengths of higher frequencies, it's easier for humans to locate the origin of higher frequency sounds than of lower frequency sounds. The auditory canal, called the external auditory meatus, has three primary functions: to control the temperature and humidity of the eardrum, to protect the eardrum from unwanted dirt particles by means of tiny hairs and a coating of wax, and to amplify sounds in the frequencies most necessary for speech and music, around 2,000 to 4,000 hertz. The eardrum, or tympanum, is a thin, tough, and surprisingly loose membrane that protects the inner hearing mechanism from the environment. It vibrates back and forth in sympathy with sound pressure waves in the atmosphere. The ear bones, hammer, anvil, and stirrup, or also called the malleus, incus, and stapes, are the smallest bones in the human body. Together, these three bones, collectively called ossicles, receive physical energy from the eardrum's vibrations, transferring it to mechanical energy and amplifying it in the process. As the eardrum vibrates in sympathy with sound pressure waves from the environment, the ossicles act as a set of levers to transfer physical energy of sound waves to mechanical energy. Three factors cause an overall increase in pressure of 80.5 times from the eardrum to the oval window. 1. The eardrum is much larger than the oval window, which causes an increase in pressure of 35 times. 2. The eardrum buckles in the middle, which doubles the pressure at the oval window. 3. The ossicles, acting as levers, increase the pressure by a factor of 1.15. Taking these three factors into account gives us an overall increase in pressure at the oval window of 80.5 times. Also, muscle actions of the ligaments supporting the ossicles combine to protect the eardrum from loud sounds. The microelectron photograph is of the stirrup or stapes. The eustachian tube connects the open area behind the eardrum to the nasal cavity. This helps release pressure from the inner ear to the atmosphere. The semicircular canals have nothing to do with hearing. They're involved in maintaining a sense of balance. This photograph shows the semicircular canals and the cochlea. The inner ear, or cochlea, is a fluid-filled spiral-shaped body containing hair cells that convert vibrations into nerve impulses. The oval window, near the base of the cochlea, transmits vibrations received from the ossicles into the fluid of the cochlea's interior chambers. This cutaway view shows the 3 fluid-filled chambers inside the cochlea. You can follow the vibration's path upward from the oval window through the vestibular canal, around the heliocatrema, and back down through the tympanic canal to the round window. The round window releases pressure built up in the cochlea. When the oval window bulges in, the round window bulges out. Energy transmitted by the round window returns to the atmosphere through the eustachian tube. The middle chamber, called the cochlear duct, contains the mechanisms that sense the vibration frequencies and convert them into nerve impulses. Within the cochlear duct, the tectorial membrane overlaps the organ of Corti, resting on the basilar membrane. Hair cells are embedded in the tectorial membrane. The basilar membrane supports 1 row of inner hair cells and 3 rows of outer hair cells. Waves traveling along the length of the tympanic canal cause the basilar membrane with its hair cells to undulate. There are about 3,500 inner hair cells resting on the basilar membrane. 93% of the fibers of the auditory nerve connect to the inner hair cells, indicating that they send more acoustic information to the brain than do the outer hair cells. But there are 20,000 outer hair cells arranged in 3 rows. Outer hair cells change their length very rapidly, which may improve oral sensitivity and fine-tuning. Higher frequency stimuli create waves in the inner ear whose point of maximum excitation is nearer the oval and round windows. We perceive these as higher pitches. Lower frequency stimuli create waves whose point of maximum excitation is nearer the far end of the cochlea, the heliocatrema. We perceive these as lower pitches. Near the oval and round windows, the basilar membrane is narrow and responds best to higher frequencies. At the heliocatrema, the basilar membrane is wider and responds best to lower frequencies. This tonotropic organization is retained in the auditory cortex of the brain, where lower tones are perceived nearer the surface and higher tones are perceived farther in. The microelectron photograph on the left shows 1 row of inner hair cells at the top and 3 rows of outer hair cells at the bottom. The photograph on the right is similar, except that various patches of hair cells are missing, most likely because of overexposure to loud sounds. This microelectron photograph is an extreme enlargement of hair cells, or cilia. This microelectron photograph shows 3 rows of outer hair cells in their characteristic V or W arrangement. This microelectron photograph of the inside of the cochlea shows healthy hair cells. This microelectron photograph shows an unhealthy cochlea with missing hair cells. Persons who have lost their hearing due to overexposure to loud sounds may have hair cells missing like this. The auditory nerve carries information from the hair cells within the cochlea to the auditory cortex in the brain via a diffuse pathway. The dorsal cochlear nucleus in the brainstem responds to higher frequencies and sorts, enhances, and encodes acoustic information to be sent on. The ventral cochlear nucleus responds to lower frequencies and sorts, enhances, and encodes acoustic information to be sent on. The superior olivary complex in the midbrain processes binaural time and intensity disparity cues from the ears to help us locate sound and create a spatial map. The inferior colliculus in the midbrain is responsible for certain forms of binaural sound integration. The medial geniculate in the thalamus sends frequency-specific fibers radiating out to the auditory cortex. One of the important functions of the reticular formation in the midbrain, sometimes called the reticular activating system, is to alert the cortex of upcoming signals. Brodmann's area 41, the primary auditory cortex, is in the superior temporal gyrus. Area 42 is the associative auditory cortex. The superior temporal gyrus is the primary auditory projection area. Lower tones are mapped nearer the surface, and higher tones are mapped deeper in the fold. Click on the highlighted keys to hear the various tones and see where they're mapped in the brain. Note that indicated locations are approximate.